Hi everybody, Mr. Neff here. Today let's talk Kepler's laws. Kepler's laws is an amazing accomplishment because of the time period in which it happened. Kepler's laws really refers to the work of both Kepler and Tycho Brahe. Tycho Brahe is the one who made the observations without the use of a telescope, by the way, and Kepler is the one who analyzed the data and noticed the patterns. You could imagine how you would feel if you were going to look at something like this. Now, this is the way Kepler published it. It would have been all handwritten and sort of everywhere when he was analyzing it. But to take a look at that and pages of that and to be able to make sense of it to the point where you could come up with three very broad generalizations about orbits the way we have here. And so you'll see that the three laws are the law of orbits, the law of areas, and the law of periods. And I want to talk about each one of those just very briefly. The law of orbits is very conceptual, areas a little bit conceptual, a little bit mathematical, and then the law of periods, the most mathematical of the three. Kepler noticed that the orbits of the planets are not actually circles. They seem circular at first. They seem circular if you don't have data to analyze. But when you analyze the data, you notice that they are actually elliptical. The sun is going to be at one of the focal points of the ellipse, and then there's just a blank space at the other focal point. Our friends over at PhET do a nice job modeling this for us, and you can see that I can have the sun and the Earth system, and if I let the thing run, well, we get this. Now, if I show you the grid and show you the path, you can see, and I'm going to make it go a little bit faster. So you can see that the days are running really fast there. You'll see that it makes a subtle ellipse, and so when it starts to close off, it disappears. But you can see how it is not a circle centered on the sun. Over on the left side, you're only about 1 3/4 blocks away, whereas on the right side you're 2. And you notice that even more if I take the mass of the sun and I would increase it some. If I increase it too much, the Earth will smash into it. But if I increase it, now you see what you're starting to notice is that it is a very elliptical shape like that. Okay. So that's our law of orbits. The law of equal areas is a neat thing, particularly for us in physics. For us, we're going to see that this means acceleration, not just a centripetal acceleration, but a tangential acceleration too, so that you're going to have two components to your total acceleration, and you're going to see that you're speeding up and slowing down as you go around the path. Now, you'll see that as we're talking about this, it almost seems like we're going to ignore the first law and we're going to talk about something that's very circular. And the pictures look that way, but it's only because of the eccentricity of the ellipse isn't very great. Now, in short, what the law of equal areas says is if you had a spot on the ellipse, so say for instance you had a spot here that was at A, and maybe and then notice this is supposed to be the Earth going around the sun. So say that was where the Earth was on maybe like June the 1st. And maybe it gets all the way to B in the month of June. And so maybe B is July the 1st. And so it traveled that little bit of distance right there. Okay, now at a later part of the year, now maybe this is C is December 1st. I know what you're probably thinking too. You're probably thinking, well, it's close there, so should that actually be summer? Well, it turns out it doesn't work that way. When we're the closest, where it's actually winter in the northern hemisphere and summer in the southern hemisphere. So December 1st. What the law of equal areas says that the area of this sector, so two straight lines to the endpoints of that, little bit of a curve on that edge makes a sort of a piece of pizza shape. The two areas will be the same if it was equal amounts of time for the endpoint. So if this was January the 1st, 1 month later, then those two areas will be the same size. And so it kind of makes sense that they would be, because this one's kind of short and fat, and this one's kind of long and not very much arc length on there. And so those two areas will be the same. all that to say, what it predicts is it predicts that over here it will be slow, and over here it will be fast. Now, a neat thing about that then is, why is that? Well, as you can see, that let's take a spot like maybe right there. The force that's responsible for all this, of course, is gravity. And so gravity is acting straight towards the center of the sun. Now look at that. If you think about this ellipse having a center point, there's two components there, see? There's a component that goes towards the center and a component that goes tangential. We all know that this component that goes towards the center is going to cause a centripetal acceleration, that is, change the direction of the velocity. And this component that goes forward is going to cause the size of the velocity to change, tangential acceleration. So of course, the velocity here is going to be forward. Velocity is forward, same direction as the acceleration. So we're speeding up as we go towards perihedron, the closest spot that you are to the sun. And then consider the other side then, maybe here we are, right here. Now the force is acting towards the sun, and you have, again, a part that's going towards the center, causing a centripetal acceleration, and a part that's going back, causing a tangential acceleration. This yellow one, of course, would be the total acceleration. And now we have a velocity that's going forward, tangential acceleration backward, so we're slowing down as we get closer to apihedron, or the farthest spot away. And then our last one is a very mathematical thing, and it tells you about what to predict for the distance and period of two things orbiting the same center. And we call this law of periods or law of harmonies. Now, when you first see it, you get turned off by it, I know. But it's actually extremely, extremely easy to use in practice. This is saying if you have two things that are orbiting the same body, so maybe it is two different GPS satellites orbiting the Earth, or a GPS satellite and the moon orbiting the Earth, or it is two planets in the solar system orbiting the sun. The two things have to be orbiting the same center. But if you have that, you can say that, all right, so here's the sun, and maybe this is Mercury, and here's Venus. And we can see then that Mercury has this smaller radius of Mercury, and Venus has this larger radius of Venus. Well, they also have periods, the time that it takes for them to go around. Period of Mercury and period of Venus. Well, they will relate to each other in this somewhat mathematically complicated way that Kepler noticed, that the ratio of the periods squared will equal the ratio of the radii squared. Again, you might say, well, isn't this an ellipse? Does it really have a radius? Strictly speaking, that you're using the semi-major axis, and so if you look at an ellipse, it has a major axis and a minor axis, and so the semi-major axis is this one. Turns out that our planets in our solar system have fairly circular orbits. They're technically ellipses, but they're fairly circular, and so you're not talking about a big difference there in practice. In principle, yes, it's a difference, but in practice, it's not very different. A quick example will make you feel better about that. Take a look at this. Jupiter is 2.5 times farther than Earth is from the sun. Find Jupiter's orbital period in Earth years. So we've got the sun, we've got the Earth here, we have Jupiter. I'm drawing it bigger because it is bigger. It's not that big compared to the sun. I'll make the sun that big. Okay, and so here is the radius of the Earth, and we know that that is 1 astronomical unit. An astronomical unit is named that because that is how far the Earth is from the sun. The Jupiter, and I haven't drawn it to scale very well, but it is 5.2 astronomical units from the sun. And so we can say it takes the Earth a period of 1 year to go around, well, how much time does it take Jupiter to go around? Well, that's pretty easy. It's period of Jupiter over period of Earth equals radius of Jupiter over radius of Earth. You're going to say, hey, aren't there powers in there? There are. And the way I always remember that is I always like to think, the T is like a little right angle like that. It's a square. And so I like to think of that being squared. And the R is kind of curvy. And so that's like a curvy 3. And that's how I remember it. So I don't have that committed to memory perfectly, but I have that little mnemonic. So I can say that the period of Jupiter squared over 1 year squared equal the radius of Jupiter 5.2 AU squared over 1 AU squared. And so, oh, I made it squared. I mean cube. Sorry about that, everybody. Don't make that mistake too. So you can see then that the period of Jupiter is going to be 5.2 to the 3/2 power, which will be 11.8 years for the period of Jupiter. So you have to admit that's not so bad. Now, the thing with this is, it's very powerful if you know both pieces of information, that is the period and the radius for one thing orbiting that center, then you can figure out the period and or the radius for another thing orbiting that center. And that's a great thing to be able to do. But there is a limitation in that, what if you didn't have two things orbiting a center? What if you only had one thing orbiting the center? For years and years, the only thing orbiting the Earth was the moon. And so there was nothing else that we could compare it with. So then what could you do there? Well, Newton took this same idea and he said, this is great, but I want to improve upon it, and I think I can improve upon it with my laws of motion. And you're going to see that in my next video on Newton's synthesis of Kepler's third law. So please check that video out.